Thank you very much. Okay, we've got sound. Can you guys hear me at the back? It's I noticed that the acoustics in here are a little bit on the kind of echoey side, but I guess it's all right. So I was just chatting before about what a confluence of ideas that we've had today. It's kind of obviated my entire slideshow. I'm a little bit annoyed actually, because I had a whole bunch of ideas, and I was furiously writing them down in the last few weeks, and I thought nobody would have thought of this. Nobody would have thought, that's so original. No one really would have thought of that. And when we had the meeting this morning, everyone was like, yes, and that. And I was like, oh no, I was just like, so I'm just repeating all the things that we talked about this morning. I apologize, it's a complete waste of time. But what I will do is maybe to rush through that a little bit and then show you some examples. We could even do a bit of live coding and see just how easy some elementary synthesis of these kind of ideas is, and what incredible opportunities we have available. Anyway, I'll go through the slides. That's me. Those of you who know what I do, it's signal processing with a slant on the sounds design of everyday sounds, ordinary objects, bouncing, rolling, scraping, crushing, sonic interaction, and the analysis and synthesis of these sounds, and how we perceive them and organize them. So I kind of thought that what we're doing today is in some ways very important. It's fun, and it's a lot of play involved, which is also important. But in a way, lots of technological advances, lots of progressions are essentially arbitrary. You know, somebody says, well, kind of this is the way it should be, and for 100 years later everyone goes, oh yeah, okay, because he said so. So this is the way it's going to be, and once we're locked into a groove, we find it very hard to get out of. I think the question that came at the end of the last talk really spoke to that idea of cultural norms. Once we've established a way that things should be, it's very difficult to get away from that. Partly because we've got an investment psychologically in things being a particular way. So, for example, we know what the sounds of we think we know what the sounds of a motor vehicle should be. Everybody between the ages of 10 and 70, when they go to cross the road, has at least 10 years of training built in. So any change is going to be difficult. When we do make a radical, I've heard the word revolution spoken several times today, or radical adjustment in a technological direction, there are side effects. The example I put up here is a silly old, but it's like DDT. You know, everybody thought that's going to be fantastic, it will save, we'll have, you know, no blight on the crops, and it turns out that there are, with complex systems, side effects. And if we've discovered anything today in our preliminary talks, this is a very complex system. Therefore, we can anticipate it being a rough road. Another question that arises is that of adaptation. We are not dealing with static or fixed qualities. We're dealing with a technological progress, which is a river of change. So we can't treat that as a fixed target. What will happen is we'll come up with something, and immediately people will begin to adapt to it. They'll adjust to particular noise levels, their thresholds for warning signals will decrease, their annoyance factors may go up or down in various ways as time goes forward. And there's always the spectre of the unknown as far as something like uptake goes. I'm reminded of many words spoken by, well, the road is strewn with the bones of pundits and futurologists who said things like, we'll only ever need 640K of RAM, and there'll only ever be 10 computers in the world. And flying cars immediately comes to mind in this context. So it may seem like we've got a very clear vision now. It may turn out that people will look back and say, do you know what, in 2012, they were thinking about putting sounds in electric vehicles. You know, We may turn out to be completely wrong, so let's approach it with that kind of humility, maybe. Okay, delving a little deeper into the subject, I've tried to identify 3 areas which are pertinent to the investigation. One is the one that's been very prominent today, which is the cultural context of what is normative and what is progressive. As we travel this road, changing these sounds, we may find that conservative forces of wanting to keep cars sounding like cars, kind of have to be overcome. On the other hand, we may find that the giddy excitement of possibility and opportunity is just too much for us to handle, and we do end up with absolute cacophony of sonic chaos, where there's an open market and people download sounds for their cars like ringtones for their phone. Now, not to rag on either of those trajectories, I think that we'll find the middle ground here, but we can identify the problems. I've just written up a bunch of... I think this business of listening and how we hear is very important to the discussion. And here's a bunch of points in the middle on sound perception, taken from Michel Chom, Choury, Huron, and a bunch of other people who have analysed listening. Another important text in this regard is possibly Warren, Bregman, McAdams, Thinking in Sound, the psychology of human audition, where we realise through these studies that there are a whole bunch of ways in which we listen. Reflexive level is things that we have absolutely no control over, like the stapedous response or blinking when a loud sound comes flinching or something. The connotative aspect is the apparent physical dimensions or properties that we infer from a sound, its size, its mass, its velocity, and so on. These, interestingly, can be encoded in many different ways. Functional aspects of sounds are often culturally normative. They may be things like a car horn means get out of the way. Functional sounds appear in many guises. They're often used to identify or locate an object in space and time. Warning sounds are a good example of functional listening. However, there are many ways in which none of these are exclusive. We do all of these in parallel to some extent. Empathetic mode of listening is very much to do with how we identify or attribute feelings or emotions to an object. So we talk about roughness, but we can talk about the aggressive sound of a car or the smooth sound of a vehicle. We don't want it to sound maybe too friendly if it's dangerous. On the other hand, there's this balance between, what we do, we anthropomorphize objects through sound, so personify them. Semantic mode, obviously language, semantic mode, but complex information at a high cognitive level can be encoded in sound sequences that are non-verbal, non-spoken. Whether or not we would develop a sophisticated enough taste or ability to discern these is kind of unknown in some ways. I'll skip the other two. I think if you're very interested in this, do investigate these listening attentional schema in listening psychology. I just want to talk about these within an slightly orthogonal context. Is that we have the inanimate realm, if you like, the unchangeable acoustics, the physics of reality, buildings, loss in the atmosphere due to geometric loss, diabatic loss, refraction, all of the many of the acoustic properties. We can't change these, they're givens, they're the laws of physics. The biological is very much psychoacoustic and perceptual, and again, we don't have an enormous amount of control over that, but we can take it into account as part of the bigger picture. possibly the two that are most changeable here, they become more flexible as we move up the realms, if you like, are the social and intellectual. We're certainly hoping that social change is involved in this journey. I should move on. Okay, one thing I thought we should identify very quickly was the interested parties in this discussion. So obviously we have the pedestrians. That was where I first came in on this discussion from a road safety point of view. Then we have the drivers. We've heard about the importance of haptic feedback in the driver's experience. The residents and the manufacturer, and these are the kind of things that they might possibly be interested in. Okay, here are the factors which seem to come up. We've talked about the acoustic and the psychoacoustic, but the psychological is also very interesting. We were talking at lunchtime about how the perceived annoyance value of a sound, it depends very much on how much one feels they have control over that sound, or some kind of agency or ability to mitigate it maybe, or also how there's an intellectual rationale about sounds. We'll say, well, I can kind of understand that sound. It's okay that there's an ambulance going by, and these guys are rushing to save somebody, so it's okay that they're making a noise. Whereas we might not feel the same way about festival or music that we don't like. So our attitudes, and there is research, I think, fields, showing that actually acoustic properties account for a very small amount of this annoyance metric. 10 or 20%. The remaining 80% is psychological. It's to do with our predisposition to the sound. Okay, we have engineering challenges. I heard earlier about placing small loudspeakers under the bumper, for example. We talked about shakers or vibrational transducers. How the transducers are mounted and how they're designed to maybe collimate sound directionally into the direction of travel, what frequencies they're able to transduce are all part of the problem. I don't think we can just see this totally in isolation as a signal processing problem without considering what happens when you try to attach a sound source which is potentially trying to make 20, 30 hertz and push it forward from a vehicle which is already moving at 80 miles an hour. It's a non-trivial engineering problem. And the area which I'm probably best educated to comment is in the computational realm, which is the modelling and analysis and modelling of sounds that we might use as vehicular engine surrogates or warning sounds. So I'm just going to quickly go through some of our interested parties. Here's the pedestrian. We talk about awareness. Awareness is a strange thing. Awareness may not be conscious. If you study when somebody's just walking through a crowd, in terms of an AI problem, that's an absolute miracle. It's the most remarkable thing. The coordination and prediction of where people are going to go, it's just, machines can't do it. And we can't even understand how somebody walks through a crowd. The reason, and this applies very much to sound, is that enormous amounts of computation are going on, and most of this with sound is utterly subconscious. It's cognitive level 1. We are not aware, oh, there's a very fast object that just moved past me at high speed. No, we just step out the way and we find ourselves standing here and, oh, how did I get here? We react to sound. So we may not be able to maybe ineffable. We may not be able to verbalize it, and that makes a very difficult design problem. So these are the things that, from a safety point of view, we're hoping to communicate to the pedestrian. The location of the moving object, its mass. How does sound convey mass? That's interesting. That can be to do with the relationships and ratios of frequencies. Its velocity. Or change in velocity, acceleration. Obviously, Doppler will give us some cues on this, but absolute velocity, make it more difficult. And it's important to design sounds for these vehicles which are differentiated from the environment. So We've talked about them being differentiated from each other, and yet at the same time that could produce a cacophony. This clashes with the problem of needing to differentiate vehicles from each other to know which ones are the ones we need to avoid and maybe the ones that we don't. Or if we're driving a vehicle, how is our internal engine sound differentiated from the other vehicles so that we can be situationally aware of them. Okay, we have this balance here then aesthetically between the thing being too noticeable and noticeable enough. Yeah, for the driver, I have a list here which involves a bunch of things that we get to know about the response of the vehicle, its behaviour. How is the transmission behaving? How is the tyre purchase on the road? How is my gearing? And this all seems normal at the moment because we're used to driving vehicles which behave like this. Thus, the bus driver says, you know, I really find this dead, this electric vehicle, and yet the question is raised at the same time, well, if you were transported 50 years into the future and your knowledge of previous vehicles was erased, would you feel the same way? No, you just kind of accept that for being normative. However, I think there are and should be more studies on sonic interaction design, usability, drivability studies to see if this improves driving performance to have these kinds of signals fed back into the cockpit. Interestingly, a completely silent vehicle on long road journeys isn't going to keep you awake. It just occurred to me that that might be an interesting problem. And there are other sorts of periphery problems. The masking sound off the engine. I was thinking about a taxi, or if you kind of get into a limousine, and the driver maybe is polite, winds up the kind of window thing. But often you'll be in the back of a vehicle, and the engine sound means that you can have a conversation in the back without the driver. You know, it's kind of part of our cultural milieu, if you like. It's part of our normative expectations. And suddenly you find yourselves in these situations, as we heard about with the bus, where, hey, it's really quiet, isn't it? Yeah? I was going to feel uncomfortable, maybe. So recreating these sounds may be part of an exercise to kind of bring things to a more normal sense. Okay, so I'll just move on to this, I think. Yeah, disturbance and annoyance. We can distinguish these two things. You can be disturbed without being annoyed, which is one reason that surveys and interviews are quite a poor tool. Cognitive performance drops enormously. We know of a lot of studies with this, mental arithmetic, concentration, and so on, all fall off rapidly. Although you may not be aware that this is happening to you, it's another ineffable kind of impact. On the other hand, your body's responding to this. Hypertension, cardiovascular stress. There is a journal which I discovered in researching this, Health and Sound, with more than scores, hundreds of very interesting articles on health and sound, which really brought home to me the scale of this and just how little it's dealt with. Okay, things which kind of help with this. Familiarity. Again, slightly to do with control. How much are we able to just shut these things out? Some spectra and some time domain signatures are much more penetrative than others. So we're able to just simply close the window and make that sound go away. That's very useful. Possibly a useful marker is spectral flux, is how much a sound changes in a short interval of time. This is something that leads us to be more aware of it and to be more annoying. And there were two measures of sound disturbance and used in relation to sound as a health hazard, which is whether or not it's periodic and sustained or whether or not the sound is impulsive. And it's interesting to note that the motor vehicle sound, at least from the internal combustion engine, falls into a grey area between these two because it's a series of explosions. Thus, at low revs, it is in nature impulsive. And yet, when the speed of the engine goes above 20, 25 hertz, becomes essentially periodic and sustained, to the extent that the part of our brain which deals with those is able to kind of threshold it down and it becomes less noticeable. So these were the concerns of the manufacturer, trying to create an identity for the product, imbuing the sounds with various qualities. We talked earlier that those qualities might not be what we think they are. That very much depends on the ambient culture. If the culture is very sort of moving towards a green, low emissions, noise-conscious, energy-efficient sort of culture, then you would wear the quietness of your vehicle as a badge of pride and be very happy, you know, that you. On the other hand, if you're kind of a petrol head, you want a roaring sound, and this is very much about your psychological projection of your values as the driver. And the prospect of accessorizing sound, which we talked about just a moment ago. A mixed blessing, certainly. Okay, so one of the things which occurred to me, not only is that we have these various actors, and there's a tension between their interests, and we have a complex intersecting realms of interdisciplinary stuff to kind of do this in. But there's an interesting tension between a purely rational approach to apply instrumental reason, which may be a terrible mistake, or to have an aesthetic, artistically informed approach to this, a design-based approach, which is more humanistic. So let's look at these two here. Taking it to the extreme, could we just model all of these factors that can be quantifiably modelled, enumerated, draw them up in a huge great graph, treat it as an optimization problem, look at the minimum point and say, that's the sound. That's the one there. So we'll have line spectrum mediocrity for the next 20 years, and all sounds will be this optimal car engine sound, calculated to serve the needs of everybody. Is that even realistic? I think probably not. I think there's too much subjectivity about many of the measurements. What would be the result of that? Almost certainly kind of more than guidelines, yeah, certainly. And we end up with this very interesting area of legislation, recommendations, manufacturing, enforcement of it, and so on. I'd like to imagine that we could solve this in a more humanistic way as a sonic interaction design problem with these interested parties involved. Experts outside of the four identified groups, and then kind of have some feedback and dialogue about these issues. So sound designers, urban planners, manufacturers, and this is where we've got to. This is kind of tracing the trajectory which has led us to this idea of a competition, that we just let everyone have a go and say, hey, this is why I think cars should sound like this, and so on. But simply doing this, I'll just go to here, go to the outcomes, raises as many questions as anything. What are going to be the rules of this? How are we going to devise assessment criteria which can be simply stated? How can we make an even playing field in terms of deliverables at realistic timescales, and so on for the competition? And after the competition, assuming that we're able to decide and give a price, what would we take from that? And what would we give back from that to all the participants? In terms of expert opinions, interview survey results, and so on. And would this lead to suggestions for future research? So how would this feed back into another cycle? Moving to just back to the technical questions about how we might go about this. Looking at the bottom there, looking at the methods first, I think there were three things we can see. One is actually just going the whole hog and modelling existing engines and seeing where that gets us. So we can use waveguides, finite element models, base our design of car engines on existing mechanics, excitation chains, resonances, and so on. Having a digital computational model then means that we can move out into hyperreality. We can tweak parameters of it. We can start to disobey the laws of physics and make it a quieter kind of engine, or one which has a more aggressive curve, so it means that once it travels past a certain velocity, its change of tonality becomes much more than it would be for the real vehicle. Thus, it becomes a stronger warning, for instance. Okay, another approach is that we abandon entirely any attempt to model the vehicle and just come up with fanciful parametric designs. We could use FM synthesis, additive approaches, granular approaches, a whole gamut of different synthesis styles and techniques. The question then is, how does the simulated engine respond to parametric data? How does it respond to the conditions of the moving vehicle? We assume that the physically based model will give us a good approximation. But what about a parametrically designed model? It certainly gives us more scope, but then we may end up with very unusual behaviours, which take a lot of acclimatization, a lot of training before we are able to understand them. Another thing that we could do for the purposes of the competition is to simply make a mock-up of the behaviour of the vehicle using any means available to us, whatever we like. Comb and paper, making a kind of rattle sound with a handle or something. Traditional sound design, where we use simile, metaphor, and all of these kind of ways to approximate behaviour that we want. Okay. In terms of the actual tools we might use, I don't want to limit this, so obviously synthesis frameworks, there's more than enough things for us to play with there. MaxMSP, Pure Data, C Sounds, Super Collider, whatever. But to be more inclusive, it may be best to simply, when we present the video, the silent video, to allow any methods at all. I think what would be key in that case is that all of the work is evidence, that multi-tracks are submitted, so that we can see how sounds have been constructed, perhaps by layers or looping or wavetable synthesis or something, and be able to analyse that and get useful information from it. Okay, so that's it for the slides. How much time do we have? A little, 3 minutes. I haven't much time to show you some examples then. So I'll just really quickly, let's have a look. So I work in Pure Data. Some of you have probably seen some of these kind of things. And one of the simulations that I have looked at before is engines. This here shows how we get these half parabolic pulses. And these pulses are actually very similar to the signature that we expect from a cylinder in a combustion chamber. When the valve opens, we get this. And it's incredibly simple to synthesize some of these. So let's see a vehicle model based on this. This is a 4-cylinder engine, which has... the trick with this one is that it has an exhaust pipe, which is a complex waveguide, and we're modelling how we excite that with this if you listen, there's a few interesting features of this. It will behave equally loudly at very low revs. So we can kind of take it all the way down to sort of unfeasibly low revs and still maintain a high amplitude. But it also encodes acceleration. As we move up, we'll hit resonances, and we can hear by the sequencing of them. So by having a model here, we've got a more complex behavior than we might have just by shifting wavetables, say. As we move up through the different speeds, we'll hit different resonant points in the waveguide. Another interesting feature is things like jitter. Most attempts at modelling engines assume that absolutely perfectly periodic signals. Most real mechanical systems no such accuracy. One of the upshots of it is that they blend much better with each other. So where we saw earlier that we go to cacophony by mixing together nominally very similar signals, when we add jitter to them, that stops. And it's one of the reasons why soundscapes of real vehicles don't jar so much, because they're actually made of these little impulsive parts which we can't predict as periodically as we think we might. So here's an example, I think, of an engine which involves jitter. It's a very toy to a game, yeah? But you can hear as it moves up this little rev meter here. And there were a few other little alternatives. We could use a turbine. Here's a turbine model. This is for a jet plane, so I'm just going to get rid of the burn. And just hear. Something like this is it's just an incredibly simple additive synthesizer, but its values are taken from a real turbine. So it's a sparse spectrum, but it gives us the right kind of impression. Yeah. And finally, I think, yeah, I just got electric motors. So we're actually able to model electric motors. This might be helpful, might be useful. Given that it's an electric vehicle, to be able to model a motor and then extend it or modify it in some way. Here we go. Not that one, that's horrible. Oh dear, maybe. Okay, I'm not going to go with that one. I'm going to leave that one alone. It's far too scary. We don't want our cars to sound like that, definitely not. Okay, I think that's just about all, really. So combining the psychoacoustics and the acoustics and the interests of the parties and our ability to model these things, I think we can find a way forward. Thanks very much.